In this video, we are going to talk about the basics of the operational amplifier. And in the upcoming videos, we will talk more about this operational amplifier and we will see how we can design the different circuits using this operational amplifier. So as its name suggests, this OPAMP is basically a amplifier, and the basic job of any amplifier is to amplify the input signal. Now let us understand why it is known as the operational amplifier. So in early days when digital computers were not evolved, at that time the different mathematical functions like addition, subtraction, integration and differentiation were performed using this operational amplifier. So just by connecting a few resistors and capacitor, it is possible to perform different mathematical operations, and that is why this amplifier is known as the operational amplifier. So now if you see the circuit symbol of operational amplifier, it can be represented by this symbol. So it consists of two inputs and one output, and most of the amplifiers consist of a two power supply, the positive and the negative power supply, but there are many op-amp ICs which runs on the single power supply. So now in this operational amplifier, the input terminal which is marked by this positive sign is known as the non-inverting input terminal, and the another input terminal which is marked by this negative sign is known as the inverting input terminal. And it will be get clear to you very shortly why it is known as the non-inverting as well as the inverting input terminals. So now if you see this operational amplifier, it is a one kind of differential amplifier with a single output. It means that this amplifier amplifies the difference between the two input signals. So let's say V1 and V2 are the input signals which is being applied to this operational amplifier, and let's say the gain of this operational amplifier is A, then the output will be equal to A times the V1 minus V2. So let's say if we have applied the single input to this operational amplifier and we have grounded the another input terminal, then at the output you will get A times V1, where A is the open loop gain of this operational amplifier. The reason it is being known as the open loop gain because it is the gain of the operational amplifier when there is no feedback from the output to the input side. So suppose if you are applying the sinusoidal signal over here, then at the output that sinusoidal signal should be get multiplied by the factor of this gain, and at the output you should get an amplified sinusoidal signal. Now here the phase of this output voltage will be the same as the input voltage. Likewise, whenever we are applying an input to this negative terminal and we are grounding the another terminal, then the output of this amplifier will be equal to minus A times the V2, because the difference between these two input terminal will be equal to 0 minus V2, that is equal to minus V2. So suppose let's say if we are applying the sinusoidal signal at the input, then at the output we will get the amplified sinusoidal signal which is having a 180-degree phase with respect to input signal. That means the output will be get inverted by a 180-degree, and that is why this input terminal is known as the inverting terminal, because the output will be get inverted with respect to input. So now here suppose if we apply the input signal between these two positive and the negative terminals, then at the output we will get A times this differential input signal, where here this A represents the open loop gain of this operational amplifier. Now this operational amplifier is very high gain amplifier, and the value of gain used to be in the range of 10 to the power 5 to the 10 to the power 6. So let's say even if we apply the 1 millivolt of signal between these two terminals, and let's say if the gain of this op-amp is 10 to the power 5, and at the output theoretically we should get 1 millivolt signal that is multiplied by the 10 to the power 5, that is equal to 100 volt. Or let's say if we apply 1 volt of signal, then theoretically we should get a output as a 10 to the power 5 volt, but that is not possible, and the output of this op-amp is restricted by the biasing voltages that is being applied to this op-amp. So the output voltage will be between this biasing voltages. So if you see the voltage transfer curve of op-amp, then it will look like this. So here the x-axis represents the differential input that is being applied to this operational amplifier, and the y-axis represents the output voltage of the amplifier, and here the slope basically represents the gain of the amplifier, which used to be in the range of 10 to the power 5 to the 10 to the power 6. Now here let's say the gain of the op-amp is 10 to the power 6, and let's say we are applying a 1 microvolt of signal. Then at the output we should get a 1 volt of signal. Likewise, let's say if we apply 10 microvolt of signal, then at the output we will get a 10 volt of output. But as we increase this input signal, then you will find that after some value of input signal, the output will be get saturated to the value plus Vset, which used to be less than the positive biasing supply. So in this way, as soon as the input voltage goes beyond some certain value, the output will be get saturated to the plus saturation voltage. And same is true for the negative input voltages. So as soon as the input voltage goes beyond some threshold value, at the output you will get a minus saturation voltage. So whenever this operational amplifier is used in an open loop configuration, that means there is a no feedback from output to the input side at that time. Even if we apply a small input signal between these two input terminals, then also you will find that the output will be get saturated towards the positive or the negative biasing voltages. So this particular characteristic of the op-amp is particularly useful when we use this op-amp as a comparator. So this is one of the application in which this op-amp can be used. But if you see this op-amp can be also be used in so many other applications, like in designing the active filters, oscillators, waveform converters, and analog to digital and digital to analog converters. And if we count the list will go on. So basically this op-amp is very versatile IC, and you will find this op-amp in so many applications. Now the reason this op-amp is used in so many applications is because of its different characteristic. So let us see the different characteristic of the op-amp because of which it is being so versatile and used in different applications. So before we see that, let us see the equivalent circuit of the op-amp. So as you can see here, this Ri is the input impedance of this op-amp. Likewise, this Ro represents the output impedance of this op-amp, and the output voltage of the op-amp will be the open loop gain multiplied by the difference between the input signals V1 and V2. So now before we see the different characteristic of the op-amp, let us see the different characteristic of the ideal op-amp. So the ideal op-amp should have this input impedance Ri that is equal to infinity, so that whatever input that is being applied between the input terminals will directly get applied to the op-amp. Similarly, the output impedance of this op-amp should be equal to 0. That means whenever we are applying the output load to this op-amp, then the output voltage should directly come across this output load. Then if you see the bandwidth of the ideal op-amp, the bandwidth of the ideal op-amp should also be equal to infinity. It means it should support all the frequencies starting from the 0 Hz up to the infinite. Similarly, the gain of the ideal op-amp should also be equal to infinite. Apart from that, whenever these two input terminals are 0, that means the input to this op-amp is 0. At that time, the output of this ideal op-amp should be equal to 0. Now, apart from these characteristics, there are few more characteristics of the ideal op-amp, that is slew rate and the common mode rejection ratio. So we will see more about these different characteristics in detail in separate videos, but let us see the basics of this different characteristic. So in a simple way, if I say the slew rate is basically how fast the op-amp is able to reach its final value, and that is particularly useful when we are applying a square wave to the op-amp. So let's say we have applied this square wave to the input of this op-amp, and at the output we are getting this output waveform that is varying from 0 volt to the V saturation voltage. So the ideal op-amp should be able to reach from the 0 volt to the Vset volt in a 0 time. So for the ideal op-amp, the slew rate should be equal to infinity. Generally, this slew rate is defined in a unit of volt per microsecond. That means how fast the op-amp is able to respond to the output voltage. Then there is another parameter which is known as the common mode rejection ratio. So let us understand very briefly what do we mean by this common mode rejection ratio. We will talk more about it in a separate video. So let's say if we are applying the same input voltage to this V1 and V2, then the difference between these two voltage will be equal to 0, and at the output we should get a 0 volt. Likewise, when we are applying a different input voltages V1 and V2 to this op-amp, then at the output, the difference between these two voltages will be get amplified by certain amplifier gain. So this common mode rejection ratio basically defines how well the op-amp is able to reject the common input voltages that is being applied to both its input terminals, and how well it is able to amplify the difference between the two voltages. And it is generally defined as the ratio of differential gain divided by the common mode gain. So for the ideal op-amp, the value of this common mode rejection ratio should be equal to infinity. So here is the list of different ideal op-amp characteristic. So the ideal op-amp has an infinite input impedance, zero output impedance, infinite open loop gain, and infinite bandwidth and slew rate. And in this ideal op-amp, whenever the input is equal to 0, then at that time the output is also 0. And this ideal op-amp has a infinite common mode rejection ratio. But if you see any practical op-amps, they used to have finite input as well as the output impedance. Generally, this input impedance is in the range of mega ohms, while the output impedance is in the range of few ohms. Similarly, the open loop gain of the op-amp is not infinity, but it used to be in the range of 10 to the power 5 to the 10 to the power 6. Likewise, for the practical op-amps, whenever the input is equal to 0, at that time also you will get some output at the op-amp. Generally used to be in the range of few millivolts. That is known as the offset voltage, and we will talk more about it in the separate video. So here is the list of different parameters and the values of different parameters for the general purpose 741 op-amp IC. So now if you see the different op-amp ICs, they are optimized for the different parameters. So let's say if one op-amp is optimized for the very high slew rate, while the another op-amp is optimized for the very high open loop gain. And if you see some other IC, you might find that it is optimized for the very low offset voltages. So depending upon your application, you need to decide which parameter is critical for your application, and based on that you can decide which op-amp is suitable for your particular application. Now so far we have seen this op-amp in a open loop configuration. That means there was no feedback from output to the input. Now in the next video we will see what happens when we provide the feedback from output to the input side. So I hope in this video you understood the different characteristics of this op-amp.